Okay, it is time for lesson 13.4, 0 and negative exponents. So far we have learned a whole bunch of different properties and different rules to help us simplify powers. We're going to continue along with those, and this time you're going to learn how to evaluate any number written to 0 power, and you're going to learn how to deal with negative exponents. Not negative x's, negative exponents. So you'll know what to do after today. We're going to start off, and I'm going to have us complete this table here to help us evaluate a pattern, which will help us determine what to do with today's information. So 2 to the third power. 2 to the third power means 2 times 2 times 2, right? And 2 times 2 is 4, and 4 times 2 is 8. And 2 squared means 2 times 2, and 2 times 2 is 4. And any number to the first power is itself, right? Now those are the ones we know how to do. We're going to use this pattern to help us figure out the rest of these, and then this pattern is going to help us understand the rest of the information for today. So if you're looking at this pattern here, this exponent's going 3, 2, 1, 0, negative 1, negative 2, negative 3. So we can see the exponent's going down by 1 every single time, and the base stays the same every single time. So whatever pattern happens should continue. And maybe you look at this and say, well, minus 4. 8 minus 4 is 4, but 4 minus 4 isn't 2. So I want to know what I can do to this number to get that number that works every time. Well, 8 divided by 2 is 4, right? So 8 divided by 2 equals 4. And if you take 4 divided by 2, it's 2, right? So in order to continue this pattern, shouldn't we just be able to keep dividing by 2? Yes. So if you take 2 divided by 2, we get 2 to the 0 power is 1. It's true. 2 to the 0 power is 1. We'll talk more in class about why that is what it is. And then from here, if I continue this pattern, 2 to the negative first power would be 1 divided by 2. And I'm not really wanting you to use any decimals as much to have this pattern make sense. So another way to write 1 divided by 2 is just like this. Right? 1 divided by 2, same as 1/2. And if we continue along this pattern, 1/2 divided by 1/2, I would take 1/2, and I would do keep switch flip, right? So it'd be 1/2 times 1/2, because 1/2 times 1/2 is the same as 1/2 divided by 2. And 1/2 multiplied by another 1/2 is 1/4. So 2 to the negative second power is 1/4. And our last step here, I want to now take 1/4 and divide that by 2, which is the same as keep switch flip 1/4 times 1/2, which would come out to be 1/8. Notice none of those are negative, right? I had a negative exponent, but I didn't end up with a negative result there at all. Now if you're looking at this, the first thing I want you to notice is that 2 to the 0 power equals 1. Basically, no matter what number I had in here, if I had a base of 3, I had a base of 4, a base of 5, it doesn't matter. If my exponents continued to go down by 1 in each pattern, any base to the 0 power is going to end up being 1. And that's our first blank. Any non-zero number, so any non-zero number means your base can't be 0, but any non-zero number to the power of 0 is equal to 1. So if you raise a number to the 0 power, it's 1. Except 0 to the 0 power. 0 to the 0 power is undefined. There's not an answer for that one. It's impossible. It's undefined. So if I asked you 0 to the 0 power, you wouldn't say that it's 0. It's not. It's undefined. There's not an answer for it. Nobody can define it. It's crazy. So using what we know so far about this whole 0 power business, let's complete this first table. So first aspect of the table, I want you to understand any number to the 0 power is 1. We'll come back and look at these other fractional answers in just a minute. So first off, 5 to the 0 power. It's not 5. Any number to the 0 power is 1. Even if my base is a decimal, 1.02 or 1 200ths to the 0 power, yep, it's 1. Even a fractional base, the quantity of negative 3/4 to the 0 power, yeah, it's 1. Are you getting the gist of this? Don't go filling out a bunch of ones just yet, though. There are some weird ones. There's always weird ones. The quantity of negative 10 to the 0 power, it's 1. And then we get to this one and you think, oh, it's 1. It's not. This means the opposite of. I don't have the parentheses wrapped around it. So it means the opposite of whatever 10 to the 0 power is. Well, what's 10 to the 0 power? Yeah, it's 1. What's the opposite of 1? It's negative 1. Yep. So if you see a negative base that is not wrapped in parentheses to the 0 power, you're going to get a negative 1. If you see 0 to the 0 power, it's not 1. What is it again? Yes, it is undefined. Please write that word. Because I know you're probably asking to yourself, do we have to write this? Yes. Yes, you do. Okay. So basically, when you're trying to write expressions in simplest form, it's not in simplest form if the exponent's negative. So you already learned that you can't repeatedly multiply the same base, that there's ways to simplify that. So an exponential expression in simplest form may not contain negative exponents or repeat bases. So when you simplify it, those negative exponents have to go away. You've already learned how to simplify repeat bases using the product and quotient laws. To simplify an exponential expression containing a negative exponent, you need to understand that any non-zero number raised to a negative power will have an answer that is the reciprocal of the base raised to the positive version of the exponent. You are allowed to have negative bases, just not negative exponents. Those are a lot of words. Let's jump back up here to the pattern so you can see what I'm talking about. Okay, so if you kind of look, here's our little middle point here, 2 to the 0 power is 1. When I have 2 to the first power, it's 2. 2 to the negative first power is 1 over 2. If I were to write 2 as a fraction, wouldn't it be 2 over 1? Yes. What's the reciprocal of 2 over 1? 1 over 2. Right? We just flipped that fraction. So when I say that, you have to understand that a negative exponent is basically the reciprocal of the base to the positive exponent. If 2 to the first power is 2, then 2 to the negative first power is the reciprocal of that. Do you see how there's no negatives in this? There's not going to be a negative result. 2 to the negative first power is the same as 1/2. If you don't believe me, type it in your calculator, and it's going to say 0.5. And if you press math, enter, then it'll say 1/2. And take a look at the others. You have 2 to the second power compared with 2 to the negative second power. 2 squared is 4. 2 to the negative second power is 1 over 2 squared, which is 1/4. And the same happens with 2 to the third power and 2 to the negative third power. We have 8, and we have 1/8. So basically, all you need to do to get rid of your negative exponent is, if it's in the numerator, push it to the denominator. If it's in the denominator, push it to the numerator. And I'll show you what that means with these examples down here. All right. Let me zoom in a little bit here. So I have 2 to the negative third power. And I just told you, this isn't in simplest form because you're not allowed to have a negative exponent. So if I were to write this as a fraction, I'd put a 1 under it like that, right? Now, in order to get this negative exponent to go away, I just simply need to push it to the bottom. I'm going to take the reciprocal of it. So 2 to the third power goes in the bottom, and when there's nothing left up top, it doesn't mean that there's a 0. There's really a 1 still there. There's a 1 as a placeholder, because I could write this as 1 times 2 to the negative third power. So basically, again, this 2 to the negative third power is in the numerator spot. I can push it to the denominator spot, and now my exponent has a positive value, and these are equal to one another. It's crazy how it works, but you saw with the patterns up there, it actually works. So now, yes, I do want you to evaluate this for me, meaning tell me the numbers that you can, tell me what they are. So 2 to the third power means 2 times 2, which is 4, times 2, which is 8. And I know that one's already up there, so now this is just proof. Okay, now this next one, instead of the 3 to the negative second power being the top, it's in the bottom. Again, I just need to do the reciprocal of that. So I'm going to take this 3 to the negative second power and push it up to the top. Now, you see how there's a 1 there? What's 1 times 3 squared? Yeah, it's 3 squared. 1 times anything is that other number. And there would be a 1 there, and it doesn't really end up making too much of a difference dividing by 1, right? So 3 squared is 9, and 9 divided by 1 is 9. So 1 over 3 to the negative second power is actually equal to 9. Crazy but true. Here, I actually have x to the negative fifth, and if you think about it, it's in the numerator spot. I need it to be in the denominator spot. So x to the negative fifth power in the top would be the same as 1 over x to the positive fifth power. And now we're done. I don't have any repeat bases. I don't have any negative exponents. Voila. In this last one, this y to the negative sixth is in the denominator spot. I can rewrite that in the numerator spot. There's already a 2 here. I don't need to move that 2. 2 is being raised to a positive exponent, so 2 gets to stay where it is in the numerator spot. Y to the negative 6 comes up top as y to the positive 6th. It would be over 1, but any number divided by 1 is itself. Alright, so now we're going to do a whole bunch of examples because in the past this has been kind of confusing, and I get it. So I think after we do a bunch, we'll be okay. So turn the page and then moan and groan. Oh, we have to do all these examples. Yes, I just want what's best for you. Okay, so we're going to simplify each of these. Your final answers may not be decimals because I don't want us just typing things in the calculator. I want you to understand this whole reciprocal relationship. So fractional form when it applies. Okay, so I have 4 to the negative second power, right? This technically would be in the numerator spot. In order to clean up that negative exponent, I'm going to push it to the bottom. So the 4 is now being raised to a positive 2 because it's in the bottom. And when there's nothing left, there's really a 1. And right here, we can go ahead and evaluate this because we do know what 4 squared is. 4 squared is 16. So 4 to the negative second power is the same as 1/16. I don't want the decimal version. I want the fractional version. All right, 6 to the negative second power is the same as 1 over 6 to the positive second power. And we know that 6 squared, 6 times 6 is 36. So 6 to the negative second power is equivalent to 1/36. 2 to the negative fourth power is equivalent to 1 over 2 to the positive fourth power. Again, when you push that to the bottom, you clean up the negative exponent. And 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2 to the negative fourth power is equivalent to 1/16. Maybe you're thinking, oh, this is not so bad. That's what I want. Okay, now I go ahead and I throw 2 numbers at you. And maybe you're flashing back to one of those product rules we learned that when you're multiplying the same base, you can bring over the base and add the exponents. Let's do that first, and then when it's written as a single power, we'll get rid of the negatives. So here's what I mean. I'm repeatedly multiplying the same base. That means I can bring over the base and add the exponents, but this time it's a negative 4 plus a positive 2. When you take negative 4 plus positive 2, you get negative 2. So 5 to the negative fourth times 5 squared is equivalent to 5 to the negative second power. Now I'm not allowed to have this negative exponent, so I need to push that to the denominator. So this is equivalent to 1 over 5 to the positive second power. And yes, 5 squared is 25, so this is equivalent to 1 over 25. Piece of cake, right? I know. We'll do a bunch. We'll do it on whiteboards. It'll be so fun. Okay. Next one, I have negative 3, not in parentheses, to the negative second power. Okay. So all we've been doing is when you see a negative exponent, if it's in the top, you push it to the bottom. If it's in the bottom, you push it up to the top. So this technically is in the top. I'm going to push it to the bottom. Have we changed any signs on our bases? Have we made positive bases negative? We haven't. The base doesn't change. Moving this to the denominator does not change the base. It changed the sign of the exponent. So we're going to keep this negative 3, but now I have a positive squared. Okay, so positive 2. All right, so this is 1 over, this is not the quantity of negative 3 squared. It's the opposite of 3 squared, which is negative 9. And I guess the best way to write this would be to put the negative sign in the middle like that. I wouldn't mark it wrong if you had it like that, but normally you see it with the negative sign right in the middle. All right, keep it going. Another one where I have the same base being repeatedly multiplied. Let's take care of that first. Bring over the base. Add your exponents. -3 plus -9. When you are adding integers that have the same sign, you add the digits and keep the sign. So this is really y to the -12th power. To get rid of that -12 and make it a +12, I need to push this to the denominator. So 1 over y to the +12th power is the same as y to the -12th power. Keep it going. All right, so in the ones we've been dealing with, we pretty much had the negative exponent in the numerator. Sometimes the negative exponent's in the denominator. And when that happens, again, all we need to do is take the reciprocal. So if it's in the bottom, put it to the top. It cleans up a dirty exponent. Because it's got that little line there, it makes it dirty. I want a positive clean 5. So this is the same as y to the 5th in the top, and that would be over 1. But y to the 5th divided by 1 is y to the 5th power. So 1 divided by y to the -5th power is the same as y to the +5th power. Okay. Now, what do we do? Now maybe you're thinking, well, this could go to the top and this could go to the bottom. Yeah, but do you see how you're dividing the same base? When we had the problem where we were multiplying the same bases, didn't we first simplify that by using our product rules, our product property? We brought over the base, added the exponents. I would recommend for these, and there's more than one way, maybe you don't like this way and you want to do it a different way, that's fine. But what I would recommend that you do, if you see you're repeatedly dividing the same base, take care of that first using those quotient rules. Meaning, bring over your base and subtract your exponents. When you take -6 minus -3, because that's what we're doing, right? It's the top one, and you're subtracting the bottom one from it. -6 minus -3, keep change, means this is -5 to the -3rd power, because a -6 plus 3 is -3. So technically, this is in the numerator spot. I need it to be in the denominator spot. So I'm going to rewrite my base, and I'm going to write my exponent as the positive version. So the quantity of -5 to the -6th power divided by the quantity of -5 to the -3rd power is the same as 1 over the quantity of -5 to the 3rd power. Say that 5 times fast. Moving along. Same kind of an idea here. I have the same exact base, right? And it's being divided. So quotient rules say, bring over the base, and you can subtract your exponents. -12 minus -10 is the same as -12 plus 10. So this is equivalent to x to the -2nd power, which is technically in the numerator spot. In order for it to be a positive exponent, I need to push it to the denominator spot, which would leave me with 1 over x to the +2nd power. Again, you're not changing any of your bases. You're just changing the location to get a positive exponent. 3 left. Never thought it would be over. We're almost there. Okay, again, I have a repeated base here that's being divided, so first things first, let's use our quotient rules. So this is the same as y to the, and you can't do 7 minus 4, it has to be top minus bottom, and 4 minus 7, or 4 plus -7, is equivalent to y to the -3rd power. Y to the -3rd power is technically in the numerator. I want it to be in the denominator so I can have a +3. So the final answer for this should be 1 over y cubed. Almost there, almost there. Okay, now I see that there's some stuff that needs to be done in the numerator before I can even use my quotient rules. So with this, step 1, I'm going to combine those m's together here. M to the 3rd times m squared. When you are multiplying the same base, bring over the base, add the exponents. There's nothing to do on the bottom yet. So this is m to the 5th over m to the -8th power. Now I have the same base being divided. So I can bring over my base and subtract my exponents. 5 minus -8 means 5 plus +8. So I get m to the 8 plus 5 is 13. I don't have a negative exponent. I'm done. There are no repeat bases. There are no negative exponents. We're good to go. All right, last one. Again, just look at this like multiplying fractions. Let's take care of the top and the bottom. I have x to the negative third times x, which remember is like x to the first power. When you are multiplying the same base, bring over the base, add the exponents. Negative 3 plus 1 is negative 2. Same thing, same base being multiplied, bring over the base. Negative 7 plus 4 is negative 3. Now for this one, I know that if I have x to the negative second power in the numerator, for it to be x to the positive second power, I can put it in the denominator. And if I have y to the negative third in the denominator, I can rewrite that as y to the positive third in the numerator. In looking at this, I have no repeat bases, I have no negative exponents. That is your final answer. We're finally done. Yay!